All right, so yeah, we have planned our news. So as for those of you in the HPC world, next week is the Supercomputing Conference in Atlanta, which is a big conference, not just for Hammerspace, but in the overall industry as GPU computing has taken hold, not just in HPC, but in enterprise. It's become a really massive conference. And so it was lovely that Tech Live is this week, that we could announce the news that we wanted to get out for supercomputing. That's what's going out at noon today. So we'll start with that news. But before I do that, Trond is a very special guest. I'll embarrass him by saying that. But so not only is he our CTO, but he's the Linux kernel maintainer appointed by Linus for the NFS kernel. Very unusual for us to bring him out into the field, honestly. He's usually writing code and doing Linux things. But we thought it would be interesting today to have him here, not just talking about this news, but we also have an announcement going out on December 3rd about all of the new advancements going into Linux related to storage services. And so we're going to talk about today's news first, and then Trond is going to go through and chat through what we're doing in the Linux world as well. And then Ryan is our MD out in Europe, so if we have any European questions, channel, he'll be here to cover that. And then we also have in the corner our field CTO, Miguel, our channel director, Giada, and then one of my marketing team members, Linda, over on the side. So lots of Hammerspace people here today. So we'll talk just a quick refresher of what the Hammerspace Global Data Platform is, jump into today's news, and then do an embargo discussion about our December 3rd news. So as a reminder, there's a lot of things that Hammerspace does that disrupt or change the way data workflows work. And the overall concept of how, if you think about really any storage system that you're familiar with, other than Hammerspace, you have the applications that sit on the top connected to the users. Data management is done from outside the storage system, third-party tool, whatever it is, Comprise, Commvault, name your data management tool. Those sit on top of the storage system. And the file system is embedded inside of the storage system. So it's an appliance that's coupled tightly with the storage itself. The reason Hammerspace is able to do a lot of the things that we do is that we've essentially changed the way these environments are architected by pulling the file system out of the storage system and presenting a global file system as the unified file system, namespace, data plane that applications and users connect with. So no longer do you have to have different rules for each storage system, a different IP address or connectivity to each storage system. Essentially, you connect the users and applications to the file system, and if data moves, if it's protected, if it's taken off of the data center into the cloud, it doesn't disrupt the users, the application's view of the view of the data. And Trond will talk later about some of this. Some of that's due to advancements of what we've done in the client software in NFS, that you can actually have a directory tree that shows your files even if they've moved around into multiple locations. But it's not just files, it's objects as well. And it makes it possible for us, because of this layer, that then to do the data orchestration, so the movement of data underneath the file system. This is done largely for placement of data in different tiers or capacity tiers of storage, or to place data local to compute. You have a data set you want to process in NVIDIA Cloud, whatever it might look like. Moving that data local to the compute in a efficient, file granular way is a piece of the data orchestration too. So half the time our customers are using us for storage tiering, half the time is to move data local to compute for processing. And then underneath is the storage system. So we've essentially just reordered how the workflow works so that you have a global persistent view of all of your data no matter where it sits, and can use anybody's storage. You can use Whitebox, you can use Isilon, you can use Azure Blob, it doesn't matter. And a lot of this you all know. I'm just refreshing because you hear from a lot of vendors. And the unifying layer of all of this is the Hammerspace Global Data Platform, where you have all of that embedded, single software license, that has all the functionality and capabilities that are built into our system. Within that, and I don't expect you to try to read this, but you do get a copy of the slides. There will be a test, 30 seconds, to see who has a really visual memory. But the key technologies that are within this, multi-protocol, so you can share data across protocols, and we are going to talk about how that works in this latest release of software that we're announcing today. Lots of users use S3 for ingest, S3 for retention, but they want to have a parallel file system interface, which we use PNFS, out to the compute nodes to have HPC processing. So multi-protocol, cross-protocol sharing of files and objects into a parallel file system. Underneath that, it has all the data services that you need to make it enterprise ready, data protection, resilience, worm, encryption. And then at the very bottom of that is the data placement so that you can automate the flow of the data without disrupting users or applications to different locations. And over time, if you have different storage tiers you want to use for performance needs, capacity needs, locality needs, that's completely abstracted. So a customer's environment, very regular. We were up in Cambridge yesterday talking to the biotech companies. Very regular situation. They have an old Isilon. It's worked fine for them, but it's coming to the end of its life. It's 7 or 10 years old. They are moving to the cloud for a lot of their processing. What they'll do is put Hammerspace in place, connect the researchers, the sensors, the instruments to Hammerspace, ingest the metadata so that we know about the data on the Isilon, and that's what the users then connect to. And when they do make the IT decision to move to the cloud, the users and applications don't even need to know it's happened. So it's a very seamless way to change technologies over time. Yep.
Just a quick question. You've got data orchestration by objective there. Mm-hmm. On the previous slide, it was data orchestration by policy.
Same thing.
It is the same thing?
Yeah.
And what do these policies look like? What sort of level?
So objectives, essentially, it's managing by code. So you can set business objectives. My objective is I have GDPR rules and data. We talk about data moving around, but you can set a rule, for example, it's a certain type of data can't leave France. You can use it for business rules around certain projects should always have a certain latency. You could have certain projects always move to archive the instant the data is created. So it's those types of things. It's based on what is the what's happening with, or what is the business rule around the data, so that it's placed in the right location to meet those rules.
And that's totally flexible, is it? Or do you have a set of policies?
We have a set of policies that grows. It's totally flexible. Our customers that have engineers and software developers write their own objectives all the time. But there's some kind of common ones that are used over and over again. So what we do is, make available, here's the ones that are already written. Our engineers will help write them. And then if we have fairly technical users, they'll just write their own. So it's a well-documented set of tools that can be as flexible as a customer wants. Like Epic Games uses us for game development, and they have a 24/7 around the globe development infrastructure. They've written their own objectives because they're a very technical company about how data moves when, to follow the sun development. That's very unique to them, but GDPR type stuff is much more common. Any other questions? Anything you want to add, Trond?
No, well, maybe just that, the whole point of objectives is really to describe the life cycle of the data. Yeah. And, as Molly said, set business objectives. But it's actually backed by a language which we call Hammerscript, which makes it very, very configurable.
Okay. So you can cover life cycle. Data destruction is one thing people leave out. So you have objectives of data destruction, can you?
We do not have objectives to set destruction, but archiving and snapshotting and that sort of thing, managing it so that you can, once you described the workflow, you should not have to really touch the data again in order to...
But you will want to store it at some point because you don't want to keep data any longer than you have to.
Right, but that's a namespace operation,
Okay.
typically, right? So that'll want to go through the front end. Yeah.
And then just this last bit on the primer for Hammerspace, then we're going to get to our news. The piece, so that last slide, which we're doing the test on shortly, on everything in Hammerspace, this is the view that users and administrators have. So you think about this environment where you have two different types of object stores, a block store, two kinds of file stores, kind of several instances in the cloud. That has historically been extremely complicated to administer, move data across, manage copies, manage compliance. And then from a user perspective, they usually only had a persistent view to a directory or a storage system or a path. What Hammerspace does is takes all of that data, puts it in a single parallel global file system, and that's what people connect to, as I mentioned. And their view then is a user can see all those shares local on their laptop, just like a standard network share. And they're actually seeing 10 storage systems in 4 different locations, for example. From an administrative perspective, they can see where is it that maybe a data mobility, a data orchestration job is running into some bottlenecks or slowing down. They can see the speed that their users are experiencing, the IOPS, the throughput, the performance. And so this is the telemetry from administrators to see how all the systems are working. We use this inside of our product to make decisions on if you have a policy on, I always need to deliver a certain throughput for a job. We use this information to say, okay, this is the storage system which can do that. Let's place the data there. So we present all that information we use for the intelligence of our data orchestration to the administrators to see how their overall environment is running. And then from a user perspective, it just looks like files. So it takes some time for customers to get used to this idea because they're used to, I have my dedicated flash system. I need to map this set of users in this projects to my flash. I have this dedicated object system for all the archive. I also do a different job to map people to that. With Hammerspace, they don't have to do that. All users and all applications are connected to everything, and then it's simply a matter of permissions on which data sets they can access, which they can make modifications on, which they can change, that type of thing. So it's a very different view of how to architect your IT systems.
And the access to this is via Hammerspace, or could you have a natural language interface for users?
The access for users is just normal protocols, NFS, SMB, S3, we have a CLI. The Hammerscript is more about managing how data moves around in the system. Users don't deal with Hammerscript. The users just see files or objects like they're used to on any other system.
What type of cost accounting have you built into this and also carbon accounting?
It's a good question. We work with, so we have, you can certainly set, here's the cost of my storage systems. But we don't keep track of, like Amazon's always changing pricing, for example. We don't have a real-time view of costs. However, we do have partners that we work with that made a business out of that. So they keep, there's AWS partners, for example, who keep track of egress, ingress, total cost of instances, and we can use that information to feed our objectives. So sometimes it's partner related. We have a partner who does GPU orchestration, so it's essentially job scheduling to different GPU clusters. They're called parallel works, that they keep that cost accounting in their system too. So it depends on what you're trying to accomplish with it. But generally speaking, we don't try to keep, if you can hard code in, this was the cost of my system, but if it's more dynamic than that, then we rely on partners for it.
If you wanted to have an objective that you would minimize carbon footprint or something like that, can you do that in your system? Was that to?
We are aware of wattage, but I don't know that you could go so far as carbon footprint. So I'd say it would be, do you want to answer that?
Well, I will point out that we are aware of the cost of moving data. And the system will actually, it's actually emulating an actuary system, an auctioneering system fundamentally. So we do, at the coding level, we do actually have pricing involved in, not just in the placement of the data, but also the mobility of the data as it, But that said, as Molly said, we don't really expose that to the customer. We don't expect them to really.
You could potentially expose it to a third party that would offer a cost accounting system or a green accounting system.
We could.
We absolutely could, yeah.
Nobody's actually answered that yet.
Yep.
With this top-down view you've got a fairly unique opportunity to bring a lot of value.
We do, and we have a massive ecosystem of partners, as you can imagine, across different verticals, different compliance requirements, those types of things. So fortunately, the way Hammerspace is coded, it's a very easy to tie in open API that we can expose anything really that a customer might take advantage of. I mean, we do a lot with metadata. We have very robust, enrichable metadata. Not only can we work with partners to add tags and other interesting metadata, but also partners can use that metadata. So there's a lot of ways that the information about the data set can be exposed for different uses.
Molly, I'm curious about you mentioned permissions, and I suppose, we're in this zero trust environment.
Right.
Many organisations are very wary about giving their users, even their admins, kind of unfettered access to their data. And obviously you have permissioning around that, but I'm curious about, you said that this is a different way of working from an admin.
It's a really good question.
How does that impact how the conversation around, does this help enable zero trust type
It does, but it's a different way of thinking. So from a very fundamental basis, we use AD for setting trust. So the good thing is whatever your permissions are in your Active Directory, that flows to Hammerspace. And then you can set, on a project basis who can do what. In a lot of ways, and I'll talk about kind of the business side, and Trond might want to add to it from the technology side. In a lot of ways, once an admin or data architect, whoever it is that we're working with, gets the concept down, they actually prefer the Hammerspace approach because you're not saying I have to set permissions on each of these isolated systems 10 times who have different ways of saying permissions. And then even worse, I make a copy of my data out of one and I've lost control of what happens to that copy. So the idea that copies of data from a zero trust environment, you have to eliminate them. Like unmanaged copies of data are very bad. They like the idea of, okay, under a single policy, a single environment, you can't copy out of it. That's good. They can set it that way. And then you're managing at a global level. The exact same permissions are set on your Isilon as on your NetApp, as on your Azure. They like that too. So it's, I think, a more consistent, holistic view from a business perspective. And then do you want to add anything on the technology?
Well, just want to point out that, from a permissions perspective, ACLs and Active Directory, they basically give you what you need in order to authenticate and manage user access. But in a global file system, you also want to manage site access. And the objectives really are designed to manage that aspect of things by, as Molly said, GDPR type enforcement. This site may not access this data. It might be able to see the metadata because of the ACLs and because of the authentication mechanism, but it won't be able to access the data because the data will not be allowed to be replicated to that site.
Well, yeah, I have a follow-up question. At the beginning, you were talking about the difference between the storage-centric and the data-centric. So obviously, when you engage, let's say, companies on a storage-centric view, it's very easy to talk with the storage-related teams within the organization. But since the data-centric view is a bit more complex in terms of who you need to engage, what are the typical personas you're engaging in the company?
It's a good question. Yeah, it's a good question. When you think about a greenfield opportunity, I'm buying a bunch of GPUs and setting up an AI environment, is usually the AI architect. When it's an enterprise that's existed for 30 years and they already have a lot of storage systems, it's usually more the CTO and storage team. And it's in a, kind of in air quotes, IT modernization project. They've have a project to go to the hybrid cloud or get away from the hybrid cloud, or they have technology that's reaching end of life and there's a buying cycle that's occurring, and they'll come look at us and say, okay, I have some storage budget. maybe this is the time to go to something more modern. So our team really talks to everyone from the CDO related to data policies, and that's all around things like setting objectives and where does your data sit? Can you make copies? Somebody who makes decisions at that level. We talk to CDOs are big influencers. In some organizations, the CDO is just talking about structured data. And it's more you're talking to people who have a cloud initiative or an IT modernization. And then if you're deploying GPUs, we're usually a part of that conversation. And that's kind of a green field that's just new to the world. So we sell in a lot of different ways. It's actually one of the more complicated things for our sales team. That's why I keep looking at our sales director. Our story, if you're just talking to a storage environment and selling against Weka and VAST, is kind of a really basic who's fastest, most efficient, for the workload. If you're talking to a CDO about data policies and which data can be used and maintain AI governance, it's a very different conversation. And we sell in all of those areas.
Do you sell template policies? Do you supply template policies people can use and modify their own uses? Do they build the policies from scratch?
Do we start with templates and then they modify usually, or how does that usually happen?
Usually that's how it will happen. The Hammerspace language is fully documented, so the users can sort of modify them to a fairly advanced level themselves. But what will typically happen is they will come to us and ask for help, because the nuances can be fairly subtle when you're not used to this way of thinking of managing data.
And I would add on the persona side, it is kind of interesting to look at how most organizations went through this, and actually we worked on this with Ben Wu, we did a project with him, but that business intelligence, BI data, that was the big wave, 10 years ago, Tableau and Snowflake and all that. Organizations seem to be now, when they call themselves a data-driven organization, they weren't thinking about their unstructured data. They were thinking about their structured data. And they're now saying, ooh, we really need to include unstructured data in that net. So I would say there's a change in the way organizations are thinking about data, where this data-centric approach really matters to them, because they now realize, oh, that data I'm going to use if I ever want to have an AI project, I need to figure out, what do I have? What is it? Where does it sit? What's embedded in it? So I'd say there's just kind of a new wave of data-centric organizations caring about their unstructured data. When we were up in Cambridge yesterday, one of the biotech companies, one of the pharma companies up there was saying, they've only cared about our structured data, and my data swamp, of unstructured data, nobody cared about until really recently. Now they do. Having technologies like what Hammerspace offers helps them to actually be able to know what's in that unstructured data and do something with it.
You need some sort of tag, don't you, for quality of data, because if you mix customer data from a low quality source and a high quality structured books to bank type source, you get the quality is the lowest common denominator. So you need to be able to tag the data with where it's come from and how much it can be trusted.
Mm-hmm. And you think about the need to understand what the data is, which has been cleaned, which has a data scientist or data engineer touched. We have really rich metadata, that can all be stored there. So that is important for sure. What is the data? Who has touched it? Has it been cleaned? Is it not? Should it be used in AI or not? That kind of thing. So that was the kind of primer reminder of what we do. Let me jump into today's news. So Hammerspace is releasing our version 5.1 software of code, or software base. So within that, there's a variety of kind of cool things that we're doing, but I'm first going to talk about the introduction of the Tier 0 technology that is now being used in some of the larger hyperscalers in the world, and is accessible really to anyone who is doing, it could be GPU computing, but it could be CPUs, ARM, anyone who has large-scale compute nodes that are not being used really efficiently in their storage environment. So what we're hearing is, As customers are deploying, we'll just use the word DGX for this conversation. They're DGX nodes from NVIDIA. They come with a fair amount of NVMe capacity built into them. Even the big national labs in the US, Gary Grider from Los Alamos, when he bought his DGX nodes, he wanted them without the NVMe because he needed his storage to be shared storage. But the way NVIDIA sets up their SKUs, you get it whether you want it or not. Here's your SKU. It's going to come with these NVMe devices and whichever GPUs you buy. So for him, it was going to go largely unused. These other types of environments that were deployed, and we can't talk about all of them by name, but thinking not Facebook, but not Meta, but other hyperscalers, started to run into the same problem of not only did they have this storage capacity in those DGX nodes, but it was going unused. They were out of capacity and were scrambling to try to go get their external storage systems shipped, delivered, configured, and installed. And then the last piece, which we all know, power is a big problem. Power has become not just a green initiative problem, but I don't have enough power in my data center to do the work I need to problem. And so anything you can do to drive efficiency of power into these systems makes a huge difference for these customers to be able to do more work, more compute. And so when you think about how much storage are we talking about, a typical GPU server has anywhere from, let's say 60 to 500 terabytes of siloed and isolated capacity that's not being used for their AI or GPU computing infrastructure. That storage, if you think about it across 100 nodes, you're starting to talk many petabytes of capacity that is sitting idle and unused. So think about that. You've spent the money, you're using the data center space, it's already up and configured, and it's not being used. And you might wonder, okay, well, why? And you guys are all smart people. There's a lot of problems with 100 GPU nodes with 100 data silos that you now have all these discrete data sets that the other GPUs, the data users can't see. That's essentially a non-starter for these environments. If you think about things like hyper-converged and whatnot, sure, you would have local performance, but you wouldn't have any kind of shared access or shared knowledge to that storage capacity. So what Hammerspace has done is made it possible now for the first time ever to transform these NVMe devices into shared storage with no additional software on the nodes. And it's a really big deal to emphasize we're not adding software on these nodes, so you don't have the noisy neighbor problem. You don't have the problem of taking resources with proprietary client software sitting on those nodes. What we're able to do because of magical things that Trond has done in the Linux kernel is our client software for Hammerspace is already running in every single modern Linux server in the world. So we can tie in across, this is the PNFS capability, by making each of these nodes just a client to Hammerspace, and all we have to do is install a metadata server somewhere in the environment to get access to that environment. So what this does is, without all the configuration time that it takes to set up external storage, using all the extra power, the extra budget investment, the largest customer we have in production today is about 600 servers today. They're planning to scale to about 1,200. And you imagine the capacity, that's like 30 petabytes of capacity they didn't have yesterday, even though they bought it, and they have today in their shared storage. Yeah?
Is this contiguous with their normal storage, so that this GPU storage is just the same as any other storage in the organization?
Exactly.
You have to keep it separate. No, it's okay. But don't the GPUs need some of that storage for their own usage?
Well, so it's an interesting point. So there's two ways you can think about it. You have extremely fast local performance to the GPU, thinking about it as like scratch or cache, whatever you want to call it. So within each server, you have high speed to the GPU as it's writing data. It's immediately not just protected, but can instantiate a move if you want to make it just a tier of your storage. So there's a couple of ways it can be deployed. But no, from your question of do the GPUs need that for their normal work, largely no. And we've validated this with a bunch of customers now that it largely goes strategically unused.
So why do the GPUs have this storage?
Because you might deploy one compute node, and as its own entity, that's great. It's like your storage and your compute together. When you do 1,000 or 100, depending on the scale, it's not so useful.
It sounds like GPUs weren't really designed for what they're now being used for.
It's evolving way too quickly. That's
Yeah, yeah.
the problem.
Yeah. So I just want to talk through the benefits here for just a minute. So unleashing this stranded capacity that happens to be extremely fast, low latency storage is great. Because it's connected to our metadata environment and our global file system, which we talked about earlier, you instantly, the data users, the AI researchers, can see the data as it's being created nearly instantly in the global file system. So you know what data has been created. They have access to it if they have the permissions immediately, even if they're not local to it. But then we've also done something that this is just like sheer magic of improving checkpointing efficiency. So when you think about how checkpointing works, typical environment checkpoints once an hour. When the checkpoint is occurring, the GPUs go idle. And Jensen has his famous statement, an idle GPU is a sin. You may or may not think that's a sin, but that's a lot of money that's sitting there idle. And when you think about what we're talking about is an average checkpoint, depending on the environment running once an hour, let's say it takes 5 minutes. That's 5 minutes out of 60. So 8% of the CPU time that's idle to checkpoint. We drop that to a couple of seconds when you're checkpointing to tier 0. So you're liberating 8% of your GPUs. If you've spent $10 million, that's a lot of money of GPU time that's available.
So I hope you've done some good work with the data centers on their power delivery, because when a bunch of GPUs go idle and come back up again, it puts immense strain on the power distribution.
Sure, but they're checkpointing anyway, right? That's happening anyway. It's just checkpointing less often now.
There's less of a gap.
It's just less time to checkpoint. Absolutely.
Yes, I heard at one point, the biggest problem in data centers right now is precisely that, people keep taking the GPUs up and down, and just that act of switching, causes disruptions on the external grid. Yeah.
That's crazy. And then,
Sorry, can everyone hear Trond at this end of the table, guys?
Oh.
No. Could you, in future, could you speak?
Yes, sorry about that.
oh, and there's a question down there too, I think.
Yeah, so does this newly claimed storage function as GPU direct?
We have a slide later which will show that a little bit. We are GPU direct, but in this case, it's actually much faster than GPU direct because it's local within the server. So GPU direct is A efficiency when you're going across networks to shared storage, but since this is local in the server, we actually don't need to use GPU direct.
Isn't that the original intent of having storage inside the server?
To make it GPU direct? I don't think so. I don't know, but from the shared storage world, they were trying to figure out how do you deliver as fast performance across an RDMA type network to external shared storage to make it feel as GPU direct as possible. And Trond may have more to say on this, but you think about whoever it is, Luster or whoever, they're not using the local storage. They're on a network as shared storage, trying to deliver local-like speed as possible. But there still is HBAs and networks and switches in the middle where there isn't in this environment. When we're acting as shared storage, we do GPU direct, though. Do you want to add anything to that, though?
Well, just maybe point out that essentially what we end up doing in these cases where the storage, the data is actually co-located with the GPU that's using it. If they're using ODirect, then they will have basically zero copy from the storage directly to the GPU. No network access needed or anything like that. So it does end up being a direct zero copy solution.
And I don't know if NVIDIA initially created GPU Direct to be an in-server thing and then it expanded to external storage systems. I'm not sure how that evolved, to be honest with you, but the external storage systems, including us, all got certified as that program to make it, taking advantage of as many direct calls into the GPU, but you still have all the networking in the middle that slows it down relative to this. Yeah, yeah.
Are we now saying that the GPUs will be on all the time because you're using the storage on them? So that if you're saying that they used to take GPUs up and down, but if you're now using the storage on those GPUs for other things, for generalized storage, it implies the GPUs always on and available, doesn't it? Or
I don't think that's the way to think about it. You know, the GPUs are run based on a workload being sent to them saying, go process now. The fact that underneath it, the storage can be used to accept that data quickly, or we maybe are hydrating some other data local to the GPU, doesn't mean the GPU is doing anything. That's all done by the workload environment.
So it's just part of the box.
Yeah.
Is switched on.
Exactly, exactly.
Yeah.
And so how this looks in our customer environments, going back to that original, like primer we are doing, is a customer has their global data environment, which includes cloud and object storage, and the tier 1 storage maybe from VAST or NetApp or whoever it's from. All that can certainly still exist. This is just a supplement. So brand new tier storage, tier 0, it's going into the SNIA dictionaries and IEEE's writing on it. It's just another tier of super fast, largely already installed storage that's coming in your server nodes that can, through our data orchestration policies, you can leave data hot on that, or you can instantly make a second copy, or tier it, or archive it off across the global data environment. And still, the users and applications always can see all of the data. Even those 100 nodes of NVMe that are sitting in the GPU environment, they can see that data instantly. So this is just a supplement to a unified global data environment. Yeah.
This is my dumb question, but I have to ask it. Sorry, is this part of the 5.1 release, the ability to use it?
It is, yeah. Yes.
Are you the only people doing this?
Yes.
It seems odd that nobody else has sort of noticed that all these storage sitting around not being used.
They have noticed, but they haven't been able to solve it. So the reason that this storage has gone largely unavailable is if you want to deploy it as HCL or direct attached storage, each of these will be their own isolated data silo. So you're going to have to figure out how to, from a workload perspective, send the job just to this storage or just to this server node and only use this storage, and then the data here to the compliance and some of the other conversations we've been having. How do you get it off there into the environment that you're doing language model training, or data scientists are accessing it, or researchers are accessing it? You have to make a copy of the data. Now all of a sudden you have this big data management hassle, and when you're talking these big environments that have hundreds or thousands or hundreds of thousands of GPUs, it's all manual and messy. The data quality issue is so substantial that they don't do it. It's just not worth it.
At the full of the sort of thing that NVIDIA would have an interest in doing for itself, and probably have the skills to do it.
Well, what they don't have is, NVIDIA doesn't write a file system. They don't have data orchestration. This is $150 million in 10 years of investment to build what we built. Yeah. It was a big project. So think about the technologies you need. A global file system. You have to have a parallel file system so that it can feed the GPUs fast. You can't load proprietary client software on the machine because you can't have the issue of taking resources from the machine. And you need data orchestration to be able to place that data and make it accessible. There's a lot of technology that build versus partner. Most companies are going partner. And we're talking, like Elon Musk's companies are using us for this because it's not solved. And they see the immediate efficiency and benefit.
But since NVIDIA is now the biggest company in the world, isn't it?
I think so.
Why doesn't it just buy you?
It might be an option. David doesn't really want to sell us, but those conversations happen a lot. I mean, we get courted a lot by system companies, and he wants to IPO this.
Probably sneeze enough dollars to buy you.
Yeah, and there's the partnership with NVIDIA, of course, is very strong, but whether they want to acquire this technology, who knows? That's not our end game by any means, but some people come up with the dollar amount, and what do you do? So
If they lose their IP, if they start moving to file systems, so it probably makes more sense to them to partner with you than to try and develop it themselves.
Yeah, I mean, the development part, it's not in a, like, trying to sound arrogant way. There's not that many people who know how to write this stuff. I mean, Trond, we have 2 Linux kernel maintainers that work for us. So we have kernel maintainers putting the code in Linux. File system people are actually hard to find. People who know how to write file systems, there's not that many of them, like, in the whole world. There's just, the talent is tough. And it generally, the rule of thumb is 10 years and $100 million to write a file system. No, even if you're NVIDIA and have the money, writing it, debugging it, getting into production, it takes time, you know, so. This market is moving crazy fast. This GPU computing market is moving fast.
When you compare this with either sort of parallel file system environments and platforms,
Yeah.
Lustre and GPFS,
So
they not do this in?
no, so the issue with them, so if you look at like Weka or GPFS or Lustre, they have a proprietary file system client, which is what makes it possible to do the parallel I/O into the shared storage environment. That alone is software that would have to be loaded on every single individual compute node. And that's one of the problems. They're like, don't you take any of my memory or any of my compute power, don't screw with that. You know, so that's a non-starter from a tier 0 perspective. And they don't have data orchestration. So these big parallel file systems are one big, super fast blob of storage. But if you want to be able to have 100 GPU servers that are all silos, they don't have a way to unify those into a namespace. They don't have the global namespace, global file system capabilities.
So you still need a shared storage.
Right, so in these environments, what they would do is want to either load their parallel file system client on the node, which some of these environments were in tried, and they said it was too much resource contention. And then they'd have their external shared storage, which we'll talk here in a bit about. You know, there's power utilization, extra network hops, extra cost. It doesn't mean these environments won't use shared storage. They will, but this in particular case study, and this is one of our production and customers, this was what they bought. They bought 20 petabytes of external shared storage. They hadn't installed it yet, and they were out of capacity and trying to do compute and scrambling. What are we going to do? Within about a week, we had 600 of their nodes up and running and 30 petabytes of shared storage now available to the compute, so they were able to keep working. At some point, they will install their external shared storage, and when they do that, it will be unified into Hammerspace. And so in that external shared storage is a combination of Lustre and Vast. It will be unified, and then they'll have 50 petabytes of shared storage instead of, if they were not to use Hammerspace, 30 petabytes of unused NVMe and 20 petabytes of external storage. And all they had to do was buy a Hammerspace software license to free that up. Do you want to add anything there?
Maybe just point out that, you know, I mean, a few years ago you had the whole hype around converged storage and compute, and, you know, which sort of claimed to offer similar capabilities. What was missing there again was the orchestration, right? You know, that's really the key to being able to make this useful. It's orchestration and, you know, access from all the nodes.
How scalable is this? So we had a conversation a while back with MinIO, to give an example, and they were talking about exabytes, hundreds of exabytes already.
Mm-hmm.
Is that scalable for you as well, or is that?
I don't know what our scale limits are exactly, but yes. I mean, the large answer is yes. We're working in environments that are, you know, just from a capacity perspective, hundreds and hundreds of petabytes today. But when you think about the performance side, feeding tens of thousands of GPUs in production, and we haven't met any performance or scale limits.
No, you know, typically we will continue to scale linearly up to several thousand data servers. You know, so we, you know, capacity is not really the problem, and, you know, performance, as long as you get, you know, as long as you have enough data servers and enough bandwidth, you know, we will generally be able to fill it.
Here's my stupid question of the day. This is all working with Linux at the bottom level, but it's not. If I have a Windows server, I can access this as a shared file system.
You can, yeah.
Yes. So I'm not limited just to using Linux.
No, the different protocols have different attributes. So a PNFS, if you're working with parallel NFS, you can have multiple files running to, shared access to single files. You can take the data out of the metadata out of the data path. With SMB or CIFS type connectivity in Windows, you don't get it's not a parallel client, but you can see, access, read, write, share, and same with S3 as well. So every application or user type can access the data, read and write, right?
Yeah, I mean, the difference there is really, the different protocols offer different scalability points. SMB is not a parallel file system. It does not have parallel file system capabilities. So you have to, have a front end, an SMB front end that can scale, with or a number of front ends that can scale with a number of clients. Of course, those front ends can sit on top of a parallel file system, and that's really how we do it in our DSX nodes.
So to the question about GPU Direct and some of the performance and efficiencies you get, this is something we've found has created a lot of interest. And I know from the back it's probably a little bit hard to read, so I'll just share kind of briefly what this is, and then you'll have the slides to look at. But traditional scale-out NAS, think NetApp, Cumulo, somebody like that. There is 10 hops from the time that data is created across the NICs, through the switch, through the NAS controller, into the storage, for the data to pass through as it's being read or write, as you do reads or writes. And this is, then you think about, okay, so what kind of innovation did GPU Direct have? So if one of those companies like NetApp or whoever has done GPU Direct, which they have, essentially you're taking one hop, so you're going from 10 to 9 by removing one of the hops at the GPU client server. And that is an efficiency in being able to connect more directly to the GPU from the NAS controller, but it didn't do anything to reduce any of the efficiencies from the controller across the shared internal networks and into the storage. So it was an efficiency on the front end of the environment, which all of us as storage companies are taking advantage of when working in GPU compute environments, but it's still, there's a lot of inefficiencies. And when you think about inefficiencies, it's not just data path retransmission time, but there's cost, there's power, there's data center space for each of those pieces of infrastructure too. You take that a step further, what VAST did using NVMe over Fabric, and they were able to reduce that down to 8 hops. So they took one more hop out by using NVMe over Fabric to again drive even further efficiency in that data path. So when VAST is talking about we're NAS, but we're much faster, that's what they've done, and they've done something beyond GPU Direct and how they're able to accomplish that. But they're not a parallel file system. So you look at Hammerspace, who has GPU Direct and is a parallel file system, and you've reduced from what VAST is doing from 8 hops down to 5. You've taken the metadata out of the data path, so you have a direct line of performance for the data path from the compute to the storage. And you've taken a lot of the networking infrastructure that's needed in scale-out NAS systems for that controller-based architecture out of the environment. So it's faster, it's more efficient, uses less power. And then when you think about tier 0, so take Hammerspace, which already is, efficient and fast, and you're doing tier 0. If you're only using the internal NVMe storage in these compute nodes for tier 0, there's one hop. There is none of this extra overhead, latency, infrastructure, power, and cost in the environment. So when you think about all the different storage systems, everyone's always pitching to you all, that's kind of how the different architectures work. And we're all trying to chase efficiencies in the data path and speed, as well as take cost out of the environment so our customers don't have to spend as much or we make more money. But that's essentially the goal of these environments. So we're in a pathological almost approach to driving efficiencies into these data paths by not by driving things into standards, by driving as much work as we can into the metadata server, taking any of the overhead out of the data path. And so this is kind of the approach that you would see with Lustre or GPFS or Hammerspace. And then with Tier 0, right now Hammerspace is the only one who's doing it. Yeah, Ben.
You talked a lot, and this question is for Trond, you talked a lot about your kernel support, right? Is there anything about the kernel that you use that is proprietary and requires patching and things like that?
No.
No, everything we do, and it's a funny thing, Trond and I were at dinner last night talking about this. He and the other kernel maintainer that we have in Hammerspace, they have to maintain their industry standard hat of they can't just do things for Hammerspace, of course. Linux has done a good job of taking and accepting and vetting submissions. He's peer reviewed by people that work for other companies and other vendors and vice versa. So it's very just standard Linux stuff. We write a lot of code. I mean, how many submissions have we done into the Linux kernel? I heard the number recently was massive, though. I mean, we've written a lot of Linux code.
Yeah, I can't remember the exact number, but for the past 10 years, primary data first and then Hammerspace afterwards were the main contributors to the NFS client, for that entire period. There are other companies that are contributing too. We're not sort of alone in the ecosystem, but we've been doing a significant part of that work.
Yeah.
Is it fair to say that every time you go through a switch, go through a hop, the speed of light goes down? So your basic, we say electricity moves at the speed of light. The speed of light's quite slow by the time you've gone through half a dozen switches. And so you're talking about not just speed, but latency, unavoidable latency.
Mm-hmm.
The more hops you've got, there's a hard limit on how low you can get latency.
That's true, but on the other hand, when it comes to bandwidth, then you are less limited. If you can read ahead or basically queue up the data, then you can make yourself and typically an AI workload is predictable. It's not always complete random access type.
But parallel processing, parallel access would be almost essential.
Yes.
So let me walk you through a scenario, and then we're going to jump over to talk about some of the other things that we're doing. So this is a real customer, scenario that we built this on. So thinking about 100 petabytes of capacity, 1,000 GPU servers, and the NVMe is already a sunk cost. What?
Numbers don't make any. I mean, I can't get my head around this.
Exactly. So that's okay because we have some smaller examples too.
Sorry to interrupt. David, you have a ton of questions as usual, which is fantastic, but I just wanted to let the presenters know that we've got about 25 minutes.
Okay. Yep, we're good. So what this looks like, and we are linearly scalable. So whether you're talking 1 petabyte, 10 petabytes, or 100 petabytes, these numbers would all be the same. So as far as relative efficiencies. So as you think about this, in these environments, if you're using external storage for your checkpoint, a typical environment would be about 200 seconds to do your checkpoint. With Hammerspace, it's about 2 seconds. So 2 orders of magnitude faster on checkpoint. And again, that's freeing up GPUs to actually do GPU work. Infrastructure cost savings. Again, whether instead of buying 100 petabytes of external storage, whatever, NetApp, Vast, Isilon, whoever you're going to use, or using the stuff because you've already bought the NVMe, it's already cabled up, it's already installed, it's already up and running on your environment, you just need the Hammerspace capacity license, you're saving about $40 million. Again, you could add external storage later to grow your capacity, but we first use what you've got that's already fast and installed. Save your money until you've used that capacity up before you buy anything. Yeah, Chris?
Could I ask you, are you comparing the external storage with GPU servers filled with NVMe drives or GPU servers empty?
Filled. So the comparison is those GPU servers already have the NVMe. They've already bought it. It's not a comparison in cost. It's just because you don't have to buy more storage.
If I go buy a big GPU server from Supermicro, I can choose to have it filled with NVMe drives or empty. Why am I going to buy Supermicro GPU servers filled with NVMe drives, which cost me more than empty GPU servers, when I'm not going to use them?
What we've found is most of the customers who are buying from NVIDIA DGX, it already has it and they can't change it.
Oh, it was there by default?
Yeah.
So NVIDIA.
Even these companies even these companies who have massive buying power with NVIDIA, like that's the SKU, that's what you get, and it comes with it.
Well, that's the price of the GPU.
But if you were going to build your own,
It's the 30K per GPU.
yeah, if you were going to build your own on Supermicro or Dell or something else, I don't know what the price comparison would be. It would be, would it be more cost effective to leave it in the server or use external? I don't actually know.
So this 40 million is against a pre-populated NVIDIA GPU
Which
server.
is what everyone, anyone who's buying DGX today. HGX is different. DGX today comes pre-populated, yeah. And, lead times are awful. They want their DGXs. They're just going to get what they get. So that's what we're running into. And so these are deployed environments. They already have their compute nodes, and they're trying to figure out how to make them more efficient. And so when you look at what the opportunity cost is, and this is one of these environments that we're saying, we're in trouble because we need to keep our compute up and running, and we're out of capacity. We freed up that 30 petabytes of capacity for them so that they could keep working. Their biggest concern was, I have idle GPUs and I'm going to get in big trouble that I can't keep my GPUs running because I'm out of capacity. This freed up capacity for them so they could do actual work on their environment.
So which is the biggest saving, power, checkpoint, or GPU?
I think it depends on where are you limited. Are you out of power or not? Do you have a workload that can keep your GPUs busy all the time? Some can. Some have actually designed their AI or their job scheduler environment where they pretty much are keeping their GPUs busy 24/7. Others don't. So others only run them a few days a week or whatever it is. So it depends a little bit on the workload and what your limitations are. The just cost savings of if you already own storage, you may as well use it before you buy more, I think is obvious and helps everyone. The power savings and the GPU hours, it depends on the workload.
So this comparison is basically utilizing the internal drives as opposed to NAS?
Right.
Okay.
Yep.
So the established customer base for this is probably in the region of dozens to low hundred of customers really at this point.
Oh, it's small because, it's not even announced or released yet. So we have pre-release customers that are running it today. Like our sales team's just being trained on it this week and things like that. So right now it's like less than 10.
But I'm just saying the potential market for you for current is this large scale training is
It's massive.
dozens. It's dozens of companies.
Of companies who have 10 to, of companies that have 10 to 100 servers, I think it is thousands actually.
Well, 10 to 100, but that's not a large scale cluster. Large scale clusters are thousands and tens of
Yes,
thousands.
however you define that, but we have customers who have 10 GPU clusters that cost them a massive amount from their perspective, and they want to use them as efficiently as possible.
Absolutely.
So
Pointing out here that
there's not a lot of customers this size, exactly. But the benefit, no matter what size company you are, so this is a 10 petabyte customer, it's the same. It's just a sliding scale. You still get all the same efficiencies and benefits. And in some cases, it's these smaller customers who, have 10 or 20 or 30 nodes, and they've spent, all the money they're going to have for the next 5 years to buy those things, that they're even more concerned about the efficiencies because they don't have these massive budgets that the hyperscalers do.
You need some messaging specific for that section rather than this very large scale training that even if you're fairly small, there's a lot of untapped value that you have.
Absolutely.
Expose it.
No, I completely agree with you. We highlight that for this because that large-scale environment is a production customer we have today. As far as who needs it, it's the masses of 10, 15, 20, 30 GPU servers. I agree with you completely. So I'm going to jump on and pass things over to you, Trond. I want to go to the 5.1. Sorry, we have some more stuff, but we're going to run out of time to go through it. But I do want to talk just a little bit about what else we put into 5.1. So the Tier 0 was a component of 5.1, which is the software release we're announcing today. We are also bringing the full capabilities of our S3 interface into the market. So some of the questions we've had through the conversation today, as data is created and shared within the global data platform, it can be ingested over an S3 interface, over standard file interfaces, whether it's SMB or NFS. And we've done some really clever stuff to be able to make it where that workload is completely transparent, where if data is being created as an object, but you want to process it back out over a parallel file system as a file, we've done all the translation within the system that is completely seamless, that no matter which application is consuming the data or creating the data, it can share it across file and object. And this has become a really big deal in the use cases where a lot of data, somebody mentioned Minio earlier today, a lot of data sits in object stores today. Object stores are fast for a single stream of data, but when you need to have parallel streams of data, or you have a really random read-write type of environment, object stores aren't great at that. So depending on what the workload is, there's cases where you want to be able to use the data that's sitting in an object store on-prem or in the cloud, but you want to be able to have the parallel performance, active read-writes types of data. We can map that data directly into a parallel file system, but still let it live in that object store where it was originally bought. There's a lot of pretty cool stuff that goes with this, and some of this, Trond, feel free to jump in. But we had to make sure that we had things like, could we tag the metadata? Did we have awareness of the metadata? Could you do things like multi-part upload? There's a complex set of technologies within the S3 interface that we had to map into a file system to really make this possible. And again, it goes back to that concept of all data in a single environment, being able to access it from any user or any application anywhere. This really helps to accomplish that. Do you want to add anything to that?
No.
Okay.
I think.
Where are you finding the major bottlenecks that you've had to solve?
I don't think we really had to solve much in the way of bottlenecks, as much as, the big problem with S3 is really, the differences in authentication compared to sort of the more traditional NAS, and sort of marrying that and getting, we do support both sort of local users and Active Directory users for our S3 server. Obviously we will want at some point to integrate, more native S3 OpenID type of solutions, but that's not a problem that we were able to solve, with the very first iteration.
Trond, could you say what you think about Minio's S3 over RDMA technology?
I haven't really looked into it. It's, marrying RDMA and S3, RDMA is really a technology for reducing latency, in my book.
It also introduces parallel.
Yes, but, S3 as a high performance solution, tends to be problematic. So, you can certainly do point solutions to try and make it.
I understand that NVIDIA is talking to object storage suppliers.
Yeah, they should.
adapting S3 over RDMA, much like GPU Direct.
Yeah, we've heard that too, that they're going to do, like, they're qualifying our S3 interface for GPU Direct. Like, that program is running for sure. And Trond is way smarter in protocols. But yes, that is happening. The idea of multi-shared file and all the other things that you want to do with the parallel file system, S3, as a fixed object, doesn't work in a dynamic environment like that. So when you're just solving for streaming to train a language model, S3 could probably do quite well. If you're doing a lot of iteration and other things, it won't do as well.
Well, and as far as we're concerned, if our customers want to use S3 for it, obviously this is the solution we will point them to. But we will also tell them that, look, there isn't a parallel file system underlying this. It also supports RDMA. It also supports GPU Direct. If you're able to adapt your application to using that interface, you will get better scalability. You will get better performance.
Our perspective on it is there's data sitting in a lot of different kinds of storage systems, and applications, some were written for file, some were written for object. We try not to force a change in the upstream application or user behavior. If you want high performance object, we have it. If you want high performance file, we have it. And not trying to jam our architecture into our customers' environments is kind of the approach we take. And we've certainly been watching what's been going on in the object space, and our S3 is also very fast and can do all the high performance, and we'll do the GPU Direct too. And that's good for data and applications that use S3. A lot don't, though. So that's kind of our take on it. But I think Minio's right. I mean, I think continuing to improve that protocol is good, but the nature of objects as fixed, you write an objects and they're written, and they're not as shareable and dynamic, don't work in all workloads either. Other things I'm just going to zip through real quickly because I want to give Trond some time. Other things in 5.1, they're very readable and understandable. We've doubled our metadata performance, so continuing to increase speed, not just on throughput and latency in tier 0, but in our metadata servers and our metadata performance. We've driven a lot of efficiencies as we're orchestrating data across environments, so moving data from one storage system to another location. We've made about a 5x improvement in the efficiency of our data mobilities environment. Data resiliency, we initially did this for Meta. It's now available in our code for everyone, where there's a 3-way HA, so extreme high availability. So if you lose big chunks of your system, there's a lot of resiliency to be able to keep the infrastructure up and running. Automated failover across multiple sites. So when you think about we're a global data environment with different storage systems, we can't rely on the storage system for availability. If we lose a data center or a node, we need to be able to fail over to other sites. Constantly updating objectives, these policies which we've talked about, making those available to our community. Yeah, question?
Yes, please. It sounds impressive. I'm just wondering if you could tell us about some Hammerspace mechanism about making sure data are immutable.
Immutable data? Yeah, do you want to cover that?
Sure. I mean, you can set, the easiest way that we support immutable data is through the setting of objectives. You can set an objective on a file that tells the system to consider it a worm type file. So that once you've finished writing it, and you close the file, it becomes immutable, unchangeable. We also have objectives that allow you to do versioning, which gives you a similar sort of effect. So this is, but that's not really a technology that is new in Thor 1.
No, that's not new. That's just, part of our technology.
Yeah.
Yep. All right, let's jump over and talk about Linux. Can I hand it to you? So that news is what we have coming out today. We're switching over to what we're announcing on December 3rd now, which, to Trond's point, some of this is already in the Linux community. If you go dig around in community pages, you can find some of this. Hammerspace we're focused on trying to educate on the new capabilities within the operating system that help in storage services, and that's the December 3rd news. And some of it is future contributions that are coming, and some have already been accepted into the kernel.
Yep. So just a quick slide to start things off, just where we see the major industry changes happening right now that are sort of influencing our thinking around storage. I mean, the first thing is the obvious one, large language models, the whole AI revolution that is in many ways bringing, it's not quite HPC, but it's HPC-like workflows, bring them out from the academia and research centers and into mainline enterprise. And with the sort of whole large language model thing, you're pulling in different kinds of data. Typically, the scale of data that you need for your training sets won't be accommodated by a single data set. They'll be pulling in various bits and pieces of information from different storage systems. So the data sets end up being fairly decentralized. They're large because, as we know, the whole scare about overtraining your AI turned out to be, entirely the wrong approach. And then, the other thing is a lot of the scale trends mean that you can no longer do everything in a single data center. As Molly mentioned, even power is becoming a problem and is limiting the size of your data center. You need to be able to use cloud solutions. You need to be able to use multi-data center solutions just in order to get the power capacity and compute that you need in order to train these models. So, I'm not going to sort of go through all of this, but this basically sort of demonstrates that essentially the whole chain sort of starts with a data collection, sort of from multiple different sources, and the need to be able to ingest data at speed, is one that we've been trying to solve through the assimilation process that we have. What this means really is that we see a move from proprietary storage to standards-based, and the reason why we do that is because we see standards is really the only way you can do things like the assimilation process. Without the ability to leave data storage in place and have it accessed directly by your data servers, you're not going to be able to ingest data at high speed. So a lot of you have probably already seen this slide or something like it. It sort of, I believe it originally came from a blog that Meta wrote about how they are using our technology. I mean, suffice to say that they're using the fact that they have a parallel file system, metadata servers, and then storage that scales linearly, to feed their 24,000 GPUs, and they're getting performance accordingly in the 12 terabytes per second.
And the requirement at Meta was that it was standard Linux. They didn't want to go, when you think about what's been going into Linux, they really wanted to be able to use their standards-based infrastructure, right?
Right. They didn't really want any proprietary software at all if they could avoid it. Our solution does involve some proprietary software in the sense of the anvils themselves, the metadata servers, and some of the orchestration software. But most of the storage, is basically managed through standard KNFSD servers that they are running, and they're managing themselves, actually. We don't manage them for them.
I think storage server equivalents of JBoss.
You could probably look at it that way. I mean, it's, what we are doing is really just, for each one of them, we are organizing placement of data on them. We're organizing mirroring across them. So yes, I mean, you could compare it to that.
What I'm thinking is this is quite different from something like a CoreWeave GPU server farm, which will have proprietary storage in there.
Yeah, indeed.
All the metrics on that are in terms of performance and scale. There's nothing there about heat production and electricity usage. Is that intended? Is that people aren't worried about?
Oh no, they're very worried. They're very worried about their power usage.
So why is that part of this thing here? Because presumably, if you're more efficient, you're not only scaling up, you're also using less power.
Well, mostly because what we wanted Trond to focus on is the innovations we're doing in Linux that's related to storage services. Like, we're trying to kind of shifting over to what we've contributed into Linux, not the whole system architecture. We're just trying to get a little bit deeper into some of the new innovations.
Right, yeah.
They cared very much. I mean, they're trying to build nuclear power plants next to their data centers and stuff. They do care, but what Trond's trying to go into is some of the latest contributions that make a standards-based approach possible, where it wasn't without these contributions.
Yeah, no, what I'd really like to talk about is really a little bit of the pipeline sort of between Hammerspace and the community. I mean, one of the things that we've been doing from the very, very start, we've been very standards driven. For a small company, we've contributed significantly also to the NFS v42 protocol. We've been contributing to the PNFS protocol. And the way that we see that is really a way of not just validating our approach, but also getting community interest in it. We would like to see a community behind the FlexFiles PNFS standard. We've been able to contribute the client to the NFS, to the Linux community, which lowers in many ways the burden of implementation for future implementers. They don't need to write their own client, if they adopt our standard. But on the positive side, on the other side, as far as our customers are concerned, it gives them the reassurance that they are not necessarily relying on a single vendor solution. That if Hammerspace were to go away, and we have no intention of doing that, then others could pick up the slack and implement the same kind of solutions. We have more of a first implementer advantage, really, rather than sort of being the sole sole keeper of the technology. So, talking a little bit about PNFS and how it's been developed. Parallel NFS was originally an optional feature of NFS. There are competing versions of PNFS. There's a block-based version, there's a NFS v1 based version, and there's the Flex Files version, which uses NFS v3 as the storage protocol. It allows for the client to essentially talk metadata only to the server, lowering the burden of lowering the load on the metadata server and removing it as a bottleneck for most of the I/O that basically goes directly to the NFS v3 server's backends, which as you pointed out, makes it similar to a JBOD in that sense. What have we been doing recently in order to improve the protocol?
And along these lines, a lot of the parallel file system companies wrote their own client because of problems in NFS. They, David Flynn, our CEO, will say NFS used to suck. We fixed it. Other parallel file systems wrote their own client to do what they needed. We did the same. We just contributed into Linux so that it's available through the community.
Right. But in order to achieve the kind of performance that we did at Meta, we had to do a fair amount of changes to the protocol. I mean, we had the basics. The fact that PNFS is a parallel file system protocol, meant that we had the ability to scale, but there were a number of bottlenecks that needed to be removed in order to achieve the kind of performance that we saw at Meta. So one of the things that we needed to do, well known from sort of NFS over the years, the metadata chatter tends to be high. So NFS v4 introduces delegations, but there's always been a flaw with the basic delegation implementation. That is that if you're doing I/O, then any stat call that's made by the client typically also ask for timestamps. Timestamps are problematic because they, in the traditional delegation model, they are driven by the data server. So it means that while you can cache almost all the metadata, timestamps force you to go to the data server anyway. So one of the things we contributed was a new delegation model that avoids that particular round trip, allows the client to own the timestamps, A time and M time, and set them. We've also been, contributing the ability to do multiple connections between clients and servers. Multiple storage nodes, reading and writing them synchronously, mirroring, and telemetry, gathering and reporting. The ability to move data while it's live accessed and being,
Sorry to interrupt. How many more slides do we have? Because we're about to bring lunch in.
We have about...
No. I think
3. I can probably reduce it to about 3 or 4 more, if that's...
But you may need to look over the catering.
That's okay.
Yes, okay. All right. That'll be fine. So I want to talk a little bit about what we've been doing very recently, sort of contributing to the NFS client. So we've talked a little bit about parallel NFS, flex files, and the ability to connect, do multiple connections to the servers. As I said, there's a new delegation model that came out recently that went through the ITF. It's still not fully standardized in the ITF, but it's close enough now that we don't expect any on-the-wire changes. So I've been able to contribute that upstream to the NFS kernel in the recent 6.11 kernel. We also managed to contribute some fast failover semantics that were needed. Meta had a requirement that we be able to fail over from one data server to another within about 9 seconds. Typically, failover times in NFS have been sort of on the order of minutes rather than seconds. So we had to do a fair amount of work to optimize the PNFS protocol to allow servers to know when they could avoid having to resilver files, etc. If the metadata server goes down while data servers are still handling I/O. In the 6.12 kernel that's coming out on Sunday, I believe, we're contributing a technology called local I/O, which is basically the foundation of some of this tier 0 technology that we talked about earlier. Local I/O is something that if the client and the server are co-located, so you've got an NFS v3 server running on the same node as your client, and typically that will happen if you have container type technologies. Then the NFS client will detect the fact that it's co-located with the server, and it can basically reach past the NFS server directly into the file system, and open the file as if it were it is a local file, and do the I/O directly without needing to go through NFS. Upcoming work, where we have a number of customers that are interested in doing erasure coding. A lot of erasure coding solutions tend to do erasure coding on the data server, which introduces a new bottleneck. If you want to have high availability, you have to have the data server basically write data across multiple backends. The requirement that we've set for erasure coding is really that the client be able to do that. By putting erasure coding in the client, you can scale to tens of thousands of clients. You can scale the bandwidth without needing to sort of beef up your backend servers beyond what they do now.
And Chris, this is something that, as you think about object storage versus file storage, what we see in these higher performance compute environments is instead of having to stream everything across networks and then do the data protection within the storage systems, there's an efficiency you can do if you do it at the client side that in the future, how people think about where data protection occurs and how do you take hops, controllers, and networks hops out of the data path, there's efficiencies that keep getting driven further into the servers that just didn't exist 10 years ago when things like object stores were being created. And it's not so much competing against, it's just how do the data architectures work and how are you trying to get efficiency from the client, and then how are you trying to get efficiency on the storage. It's just different approaches.
Yeah, indeed. So other future contributions, we've been asked to be able to do striping. Again, this is HPC-like workflows that are sort of driving things. A lot of the workflows there are concerned with writing, having multiple clients writing to a single file. So we're interested in being able to allow those clients to access the files efficiently without requiring multiple copies of the file. That's how we do this kind of thing today. If you're reading the same file, replication of the data will typically solve a lot of the bottlenecking problems. But if it's sort of several thousand clients and sort of petabyte scale files, really the only solution is to use striping.
Sorry, Trond, we really need to wrap up.
Yeah.
Excuse the pun, but we're eating into the lunch break.
Okay, sorry. Yep. So the last thing, is just fixing the security model that you have. Being able to use TLS to protect the data on the wire, and ensuring not just privacy but also integrity of the data.
Is there a white paper or something doing this in more detail?
We can
Yes.
send that out, yeah.
Yes, please do.
Yeah.
All right. So yeah. So essentially, what we want to enable is this kind of architecture, where you have, again, the Hammerspace global file system being able to serve as the front end for, all of these workflows, burst workflows, cloud, front ending, all the back end storage, that's being ingested, and presenting it, through the platform, through our front ends, and through native NFS v4.2.
And we thought it was important to at least spend a little time with this. We'll be spending more over time.
Can you go back a slide? I
Yeah.
think a couple of people were trying
Yeah.
to take a picture.
So we're trying to spend more time on this, that it is a shift on versus proprietary storage infrastructures kind of controlling the way data architectures work. Those still exist, but as you think about a data-centric approach, being able to do more from standard Linux machines, every DGX has Linux on it, pretty much everything has Linux on it, instruments, microscopes, things like that. So being able to connect them directly into a shared data environment instead of each of them getting their own specialized dedicated storage is the way things are starting to shift. And it's important, I think, to evangelize what's going on in the Linux operating system world to make this possible, because it's a big change versus how data centers and data architectures were done 10, 20 years ago.